Welcome back to AI.Code.Cast, where we dive deep into coding problems and the algorithms that make them tick.
I love that make 'em tick.
Today, we're going to tackle a classic problem, one that's, well, it's kind of fundamental, string matching.
Ah,
Picture yourself, you're searching for a specific word, but it's buried in a gigantic document. That's string matching in a nutshell. It's like finding a needle in a haystack, but with text.
and what's fascinating is how this seemingly simple idea of string matching, it pops up everywhere.
Oh, absolutely.
It's the backbone of so many things, from search engines, the ones we use every day, to bioinformatics, which can get really complex.
It's true. Think about it. You could be a digital forensic analyst.
Yeah.
Sifting through mountains of data just to find a single incriminating phrase. Or maybe you're a geneticist searching for a specific DNA sequence, like a tiny little needle in a massive genome haystack.
In those cases, every millisecond counts.
Absolutely. So let's lay out the challenge for today. We have a haystack, which is our big old string of text, and a needle, which is the smaller string we're hunting for. How do we find that needle, that first occurrence in the haystack, and do it as efficiently as possible?
Especially as our data sets just keep growing and growing, finding efficient solutions is becoming, well, it's more crucial than ever.
Right. It's like the haystacks are getting bigger and the needles are staying the same size. Okay, let's jump right into it. We've got a ton of community-submitted solutions to look at today. Where should we start?
Well, I always think the best way to really wrap your head around a problem is to start simple,
Okay.
even if it's not the most, elegant or efficient solution in the end. So let's start with the brute force method, the good old brute force.
All right, brute force. So I'm picturing sliding a little window, the same size as our needle, across the entire haystack, one character at a time.
Yeah, exactly.
It's easy to understand, but I can already see how it might get really slow, especially if we're dealing with huge strings.
Oh, absolutely. You're right on the money. Brute force, it's essentially trying every single starting position in the haystack to see if our needle is hiding there.
Yeah.
And yeah, you end up doing a lot of, well, unnecessary comparisons, especially with a longer needle.
So let's say our needle is like 5 characters long and our haystack is, I don't know, 1,000 characters long. Are we talking about thousands of comparisons in the worst case scenario?
Oh yeah, you're picking it up quickly. In the absolute worst case, yeah, you might end up doing almost 5,000 comparisons. And that's a lot of work for, a computer to churn through. Plus, it only gets worse as that haystack keeps growing.
So brute force is kind of like our starting point, a way to understand the problem.
Right.
But it's not really a practical solution if speed is, super important.
Yeah.
But I'm looking at the community submissions here, and it seems like several folks have tried to optimize this brute force approach. Solutions 3, 8, and 15, to be specific. So what kind of clever tweaks are they making?
Let's take a look at solution 3. Instead of just blindly checking every single position, it tries to, be a bit smarter.
Okay.
It considers the lengths of the string, so it skips over any substring that's just too short to even possibly contain the needle. It avoids making new substrings for comparison, just compares the characters directly within the haystack using a sliding window.
So we're cutting down the number of places we need to check and also making the comparisons themselves more efficient.
Exactly.
That's pretty clever. Squeezing out some extra performance without overhauling the whole approach.
Exactly. And these optimizations can really make a difference, especially for, strings that aren't astronomically large. But even with these tweaks, the fundamental, the time complexity, it remains the same. It's big O of m times n, where m is the length of the haystack and n is the length of the needle.
Okay.
The space complexity, that stays constant, big O of 1.
So we've made brute force a bit smarter, but we're still potentially doing a comparison for nearly every character in the haystack in that worst case scenario. So is there a way to just skip those redundant comparisons altogether?
That's where those more advanced algorithms come into play. Now take a peek at solution 2. What do you notice about that one?
This one leans heavily on a built-in function called IndexOf. Is that even allowed? Feels a little like cheating.
Not at all. Sometimes the most elegant solution is leveraging those tools that are already at our disposal.
Right.
And these built-in functions, they often have years of optimization packed into them, so they can be incredibly efficient.
Okay, so IndexOf is doing the heavy lifting for us.
Yeah.
But how does it work its magic?
Well, at its core, IndexOf is designed to pinpoint the first occurrence of a specific substring within a larger string. Now, the inner workings, those can vary a bit depending on the programming language, but many modern implementations, they're surprisingly sophisticated. They use these, advanced algorithms behind the scenes.
Oh, okay.
So think of it as a shortcut that saves us from reinventing the wheel.
I see. So we don't necessarily need to, like, dissect IndexO to use it effectively.
Exactly. The beauty is we can kind of trust that the language designers have taken care of those nitty-gritty details, the optimizations, and in many cases, using IndexOf, it'll actually outperform a hand-coded brute force method, especially if we're talking about large strings.
Gotcha. But I'm guessing there might be a trade-off here, right? We're giving up some control by relying on a function that we don't fully grasp.
That's a valid point. We are relinquishing some control over that underlying algorithm.
Right.
But the benefits in terms of simplicity, how easy it is to read, and often performance, they can outweigh that concern in many real-world situations.
Okay, that makes sense. What about performance in terms of time and space complexity? How does IndexO stack up against, what we've seen so far?
In the worst case scenario, it's generally considered big O of m times n, which is similar to our optimized brute force approach. But remember, many IndexOf implementations, they use these clever optimizations, so the actual performance could be much better in practice.
Right.
And the space complexity, that's generally constant because we're not building any new data structures. So that's good.
All right, so it seems like IndexOf can be a real time saver and simplifies our code. But I'm now curious about some of those fancier approaches I'm seeing in the community submissions. Solutions 5, 11, and 17, they all use something called the Rabin-Karp algorithm. What makes this one special?
Rabin-Karp, it takes a different approach from what we've discussed so far. It leverages, well, the power of hashing, and that can really speed things up.
Hashing, that sounds a bit intimidating. Can you break it down for us?
Okay, so think of a hash function as a way to create a unique fingerprint, right, for a piece of data. In our case, our strings. Instead of comparing those whole substrings character by character, which can be slow, Rabin-Karp, it calculates a hash value for each substring in the haystack, each substring that's the same length as the needle. Then it compares these hash values to the hash value of the needle itself.
So we're basically converting our strings into these numerical fingerprints and comparing those instead of the actual letters.
That's the gist of it. And the really clever bit is the use of a rolling hash. So instead of recalculating that entire hash for every single substring, which would still be time-consuming, Rabin-Karp, it updates the hash as we slide our window across the haystack.
Ooh, I love a good analogy. Is there a way to visualize this rolling hash?
Imagine you've got this conveyor belt, and each item on the belt is a character, right? As the belt moves along, we add the value of the new character entering on, say, the right side of the belt, and subtract the value of the character that's leaving on the left. This gives us a running total, which represents our updated hash, all without having to re-add everything from scratch.
That's a brilliant way to put it. So we're always updating our hash based on which character is entering and leaving our little window. But what about those situations where two different strings could end up with the same hash value? Wouldn't that lead to, like, false positives?
You're spot on. That's a crucial point. And that's why there's a final character-by-character check in place. So if those hash values match, then we perform a full string comparison, just to be absolutely sure it's a genuine match and not just a fluke of the hashing process.
Okay, so we're doing a quick hash comparison first, and only if those fingerprints match do we do the more detailed character-by-character check. That seems pretty efficient. So what are the main advantages and limitations of this Rabin-Karp approach?
Well, one of the biggest advantages is its average case linear time complexity. In many situations, Rabin-Karp performs really well. We're talking a time complexity of big O of m plus n, where m is that length of the haystack and n is the length of the needle. And that's because those hash comparisons are super fast, and we only do that full character comparison if there's a hash match.
Right, that's a big improvement over the brute force methods. But you said average case, so are there scenarios where it might not be as fast?
You're right to be cautious. While the average case is excellent, in the worst case scenario, if we have a ton of hash collisions, the time complexity could degrade. It could go back to big O of m times n, which is similar to brute force. And the choice of hash function, the actual mathematical formula we use for hashing and the modulus we use for our calculations, those can significantly impact performance.
Okay.
A poorly chosen hash function can make those collisions more likely.
So it's a powerful tool, but it's crucial to be aware of those potential worst-case scenarios and pick a good hash function.
Exactly.
Hmm.
It's a great example of why understanding those nuances of an algorithm is so important when we decide when and how to use it.
All right, before we move on, there's one more algorithm that keeps popping up in the submissions, and well, it has a bit of a mouthful of a name.
Yeah.
The Knuth-Morris-Pratt algorithm, or KMP for short.
KMP. Yeah.
Solutions 4, 10, and 16. They all use this approach.
Yeah.
So what's the secret behind its popularity?
The KMP algorithm is all about eliminating those redundant comparisons completely. And it accomplishes this by using a pre-computed table. Sometimes it's called the ELPS array or the failure function. It acts as a guide, telling us how much to shift the needle forward if we hit a mismatch, so we don't have to backtrack unnecessarily.
I see how that could be huge for efficiency.
Yeah.
But this ELPS array, it sounds a bit mysterious. Can you walk us through how it works?
Absolutely. Let's say our needle is A-bab-bab. The ELPS array helps us answer this question. If a mismatch occurs at a certain position in the needle, how far can we shift the needle to the right without missing a potential match? Each element in the ELPS array corresponds to a position in the needle. And the value at that element, it tells us the length of the longest proper prefix that's also a suffix up to that position.
Okay, I think I'm following so far, but can we get a concrete example?
Yeah.
How would we build this ELPS array for that specific pattern, A-bab-cab?
Sure thing. Let's break it down step by step.
Perfect. Our listeners are ready to dive into the details.
All right, so let's start building this ELPS array. The first element, ELPS, that's always going to be 0, because a single character can't have a proper prefix that's also a suffix.
Makes sense. What about the second element, LPS1?
For AB, the longest proper prefix that's also a suffix is empty, so LPS1 is also 0.
All right, so you've got 0, 0 so far. What about LPS2 for ABA?
Now for ABA, the longest proper prefix that's also a suffix is A, which has a length of 1, so LPS2 is 1. We're starting to see the pattern here.
I think I'm starting to get it. We're basically looking for the longest repeated sequence at the beginning and end of each substring.
You got it. And this pattern continues as we build the rest of the array. So for AB, the longest matching prefix and suffix is AB with a length of 2, so LPS3 is 2.
So we're up to 0, 0, 1, 2. This is really cool.
It is, and the process continues. For ABABA, the longest matching prefix and suffix is ABA with a length of 3, making LPS4 equal to 3.
I'm curious, how does this ELPS array actually help us when we're searching? Can you give us an example of how it comes into play?
Absolutely. Let's imagine our haystack is ABAB-ABCAB, and our needle is, as before, ABABCAB. We start comparing characters from the beginning of both strings. Now, if we hit a mismatch, instead of moving the needle all the way back to the start of the haystack and comparing again, we consult our trusty ELPS array. It tells us how far to shift the needle forward based on the length of the previously matched prefix that's also a suffix.
So we're skipping over parts of the haystack where we know there can't be a match, right?
Exactly. For instance, let's say a mismatch occurs at position 5 in the haystack where we have an X, but the needle is expecting a C. We look at the ELPS value for the character before the mismatch in the needle, which is B at index 4.
So we look at LPS3, which is 2, if I remember correctly. What does that 2 tell us?
That 2 tells us we can safely shift the needle 2 positions to the right. Aligning that AB prefix of the needle with the AB we've already matched in the haystack, we don't need to check those positions in between because the ELPS array guarantees there's no chance of a match there.
Okay, I'm really starting to see the power of this approach. We're basically fast-forwarding through the haystack, skipping all those unnecessary comparisons.
Precisely, and that's the beauty of KMP, that clever use of the pre-computed ELPS array. It gives KMP remarkable efficiency.
Amazing. Before we wrap up this part, can you remind us of the time and space complexity of KMP?
The beauty of KMP lies in its linear time complexity. It's big O of n, where n is the length of the haystack, which means it scales really well even for very, very long haystacks. The trade-off is that the space complexity is big O of m, where m is the length of the needle, because we need to store that ELPS array.
Right.
But in most practical situations, the needle's length is relatively small compared to the haystack, so that extra space it's a worthwhile investment for those massive speed gains.
KMP seems like a really elegant and efficient algorithm for string matching. But as we've seen throughout this deep dive, there's no one-size-fits-all solution.
Exactly.
Let's move on to some of the more unique approaches in the community submissions and see what other insights they offer.
Sounds good.
So, looking at the remaining solutions here, it's clear our community, they love a good challenge. We've got some pretty unconventional approaches mixed in here.
That's what I love about this. It's not always just about finding a solution. It's about exploring those different ways of thinking.
Exactly. Solutions 1, 6, 7, 12, and 18, they all take paths we haven't talked about yet. Solution 1, for example, it uses recursion.
Recursion.
That always feels a little bit like going down a rabbit hole to me.
It can be, yeah. But it can also be a very elegant way to break a problem down.
Okay.
So in this case, the solution, it checks if the needle is right there at the beginning of the haystack.
All right, so we're peeking into the first layer of our problem. What happens if the needle's not there?
Well, then the function calls itself again.
Oh, okay.
But this time, it calls itself with a slightly smaller haystack. It's like, those Russian nesting dolls? We're unwrapping them one layer at a time.
I like that. Okay, so it keeps going deeper and deeper until it either finds the needle or it runs out of layers. Recursion could be tricky, though. Isn't there a risk of stack overflow?
Yeah, that's a valid concern. Stack overflow, it can happen if a recursive function calls itself too many times and it exceeds the available memory for the call stack. But in this specific scenario, the maximum depth of our recursion is limited by the length of the haystack.
Right.
So as long as we're not dealing with, an insanely long haystack, recursion should be fine.
Okay, good to know. How does this recursive solution stack up in terms of performance?
Well, the time complexity, it's actually similar to the brute force approaches around big O of m times n. And the space complexity, because of those recursive calls, it can vary a bit depending on the implementation and how deep that recursion goes.
All right, that makes sense. Now, solution 6, it takes a completely different approach. It relies on regular expressions, or rejects, as they're often called.
Rejects.
Those can be super powerful, but man, they can also be a bit intimidating.
They do have a reputation for being a bit cryptic, yeah.
Yeah, but they're really versatile when it comes to defining patterns in text. So in solution 6, the approach builds a regular expression that represents the needle, and then it uses that regex to search the haystack. It's like creating a custom search pattern just to find exactly what we're looking for.
Exactly. And lots of programming languages, they have built-in support for regex, often with, really optimized engines. So that can lead to surprisingly efficient string matching, especially for those complex patterns.
But I imagine there's a trade-off here, right? Like in terms of readability. Like how easy it is to actually understand the code. Because regex can be pretty tough to decipher, even for experienced programmers.
That's true. Regex can get pretty complex, especially for those, really intricate patterns. And it might not always be as efficient as those specialized algorithms like KMP, depending on the situation.
It's a powerful tool, but important to be mindful of those trade-offs. Okay, now, solutions 7, 12, and 18. They seem to share a common thread here. They're all using bit manipulation techniques.
Bit manipulation.
That's an area that often sends chills down the spines of even the most seasoned coders.
It can be a bit daunting. It involves working directly with that binary representation of data, manipulating individual bits. And in the context of string matching, these solutions are using bitwise operations to create very compact representations of the strings and compare them at the bit level.
Okay, I'm going to need you to break that down a little bit further for me. Can you give us an example of how bit manipulation might be used for, string matching?
Sure. Imagine using a technique called bit masking, right? We create a bit mask for the needle, where each bit corresponds to, the presence or absence of a particular character. And then we iterate through the haystack, creating similar bit masks for each substring of the same length as the needle.
So we're turning our strings into patterns of ones and zeros based on the characters they contain.
Exactly. And then we can use that bitwise A&D operation to compare these masks super efficiently. If the bitwise A&D of the needle's mask and a substring's mask are equal to the needle's mask, it means all the characters in the needle are present in that substring, so it's a potential match.
That's really clever. Exploiting the way data is represented at like the most fundamental level.
Yeah.
But I imagine these bit manipulation solutions, they can be really challenging to write and debug.
You're right. They do require a good understanding of, binary representation and bitwise operations. And as we've talked about, readability can be an issue. But in specific cases, bit manipulation can lead to some significant performance gains, especially for those, massive data sets or when minimizing memory usage is super important.
So it comes down to choosing the right tool for the job.
Right.
Weighing the trade-offs and considering the specific requirements of the problem we're trying to solve.
Absolutely. That's the key takeaway here. The beauty of algorithms is understanding these trade-offs and making informed decisions. There's rarely a single perfect solution. It's about selecting the most effective approach for that given situation.
Well said. So we've covered a lot of ground today, from that simplicity of brute force to the intricacies of KMP and Rabin-Karp, and we even went down the rabbit hole of bit manipulation and regular expressions.
It's been quite the journey, exploring that landscape of string matching algorithms. Hopefully, our listeners have a new appreciation for all the different ways this fundamental problem can be tackled.
Absolutely. And beyond just the specific algorithms, we've talked about the importance of, considering things like code readability, maintainability, and those performance trade-offs.
Right. And the unique characteristics of the data that we're working with, those are crucial considerations for any coder.
Yeah. Because after all, the best algorithm isn't just about theoretical efficiency. It's about finding that right balance, between performance, clarity, and practicality for the task at hand.
Couldn't have said it better myself.
Well, I think it's time to wrap up this deep dive into the world of string matching algorithms.
It's been a pleasure exploring these solutions with you, and of course, with our amazing AI.Code.Cast community.
To all our listeners out there, keep experimenting, keep learning, and keep those algorithms humming. Thanks for joining us on the deep dive. All right, so we've covered some really interesting ground here, from brute force to Rabin-Karp, KMP, even bit manipulation. But I'm curious, from all of these different approaches, is there one that you find particularly elegant or maybe surprising in how it tackles the problem?
That's a good question. I think for me, the elegance is often in the simplicity. Like that IndexOf solution,
Oh, yeah.
it might seem, almost too simple at first glance, but it highlights a key principle in problem solving. Don't reinvent the wheel if you don't have to.
Absolutely.
And the fact that these built-in functions often leverage sophisticated algorithms under the hood, that's pretty cool. It shows the power of abstraction, right? We can achieve great results without having to get bogged down in every single detail.
Right. It's like standing on the shoulders of giants. Someone else has already figured out that really complex part for us.
Exactly. And on the other hand, sometimes it's the more intricate algorithms that really capture my attention, like KMP with that ELPS array.
Yeah, KMP is pretty slick.
It's so clever in how it uses that pre-computed information to completely avoid those unnecessary comparisons. It's a beautiful example of, trading a bit of space, that ELPS array, for a significant gain in time. And in many cases, that's a trade-off that's well worth making.
Especially with those massive data sets we're dealing with these days.
Exactly.
Well, we've talked a lot about algorithms in the abstract today, but in a future AI Codecast, maybe we can explore how these algorithms actually play out in real-world applications.
Oh, absolutely. I'd love to dig into that.
How they power things like those super fast search engines we use every day, or how they help geneticists analyze massive amounts of DNA data.
Yeah, the applications are endless. It's exciting to think about.
It really is. Well, to all our listeners out there, thanks for joining us for this deep dive into the fascinating world of string matching algorithms. And remember, keep coding, keep experimenting, and most importantly, keep having fun.
Couldn't have said it better myself. See you next time.
See you next time.